What is black hole? A black hole is a region of space where gravity is so strong that nothing, including light, can escape its pull. It is formed when a massive star runs out of fuel and collapses under the force of its own gravity, creating a point of zero volume called a singularity. The gravitational pull around the singularity is so strong that it warps the fabric of space and time around it, creating a point of no return called the event horizon. Any object that crosses the event horizon is pulled inexorably toward the singularity, and once it passes the point of no return, it can never escape. Because black holes do not emit light, they are invisible to the naked eye, and their existence is inferred by their gravitational effects on nearby matter. Black holes come in different sizes, from stellar black holes that are a few times the mass of the Sun to supermassive black holes that are millions or billions of times the mass of the Sun, and they play a crucial role in shaping the evolution of galaxies and the universe as a whole. Formation and evolution. Black hole. Black holes are formed when massive stars run out of fuel and collapse under their own gravity. When a massive star reaches the end of its life cycle, it no longer has the energy to sustain the nuclear reactions that create outward pressure, and the force of gravity causes the star to collapse in on itself. This collapse generates enormous heat and pressure, which can cause the star's core to collapse into a singularity, a point of zero volume and infinite density. The size of the black hole that forms depends on the mass of the star. Stars with masses less than 3 times that of the Sun typically end their lives as white dwarfs, while stars with masses between 3 and 8 times that of the Sun become neutron stars. Stars with masses greater than 8 times that of the Sun can collapse into black holes. Once a black hole is formed, it can continue to grow by absorbing matter from its surroundings. When matter falls into a black hole, it forms a disk of hot, glowing gas around the event horizon. This disk can emit intense radiation, making the black hole visible to telescopes. Over time, black holes can merge with other black holes, forming larger and more massive black holes. Supermassive black holes, which can have masses millions or billions of times that of the Sun, are thought to form through the accretion of matter and the mergers of smaller black holes. These supermassive black holes are found at the centers of most galaxies, including our own Milky Way. Black holes also play a crucial role in shaping the evolution of galaxies. As matter falls into a black hole, it releases enormous amounts of energy in the form of radiation and jets of particles that can heat and ionize gas in the galaxy. This feedback can regulate the growth of galaxies and influence the formation of stars. Structure of black hole. The structure of a black hole is characterized by 3 main components: the singularity, the event horizon, and the ergosphere. The singularity is a point of zero volume and infinite density located at the center of a black hole. It is where the laws of physics as we know them break down, and our current understanding of the universe cannot explain what happens there. The event horizon is the point of no return around a black hole, beyond which anything that crosses cannot escape. It marks the boundary of the region from which nothing, not even light, can escape the gravitational pull of the black hole. The size of the event horizon is determined by the mass of the black hole, and for a non-rotating black hole, it is proportional to the mass. The ergosphere is a region outside the event horizon where spacetime is dragged along by the rotation of the black hole. Within the ergosphere, particles and energy can escape from the black hole, but anything that crosses the boundary is still inevitably pulled into the black hole. The size and shape of the ergosphere depend on the spin of the black hole, and it is largest at the equator and smallest at the poles. The structure of a black hole is determined by its mass, spin, and charge, which are the 3 properties that characterize a black hole. A non-rotating, electrically neutral black hole is described by its mass alone, but in general, black holes can have different combinations of mass, spin, and charge, which determine their properties and behavior. Gravitational collapse and black holes. Gravitational collapse is a phenomenon that occurs when a massive object, such as a star, runs out of fuel and can no longer produce the energy needed to counteract the inward pull of gravity. As a result, the star's core collapses inward, leading to an explosion known as a supernova. If the star is massive enough, The collapse can continue even after the supernova explosion, eventually leading to the formation of a black hole. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape its pull. The boundary around a black hole beyond which nothing can escape is called the event horizon. The size of the event horizon is determined by the mass of the black hole, with more massive black holes having larger event horizons. Black holes are some of the most fascinating objects in the universe, and their study has led to many important discoveries in physics and astronomy. While they may seem mysterious and even frightening, they also offer important insights into the nature of space, time, and gravity. High-energy collisions can potentially create black holes, although the likelihood of this happening depends on a variety of factors, including the energy of the colliding particles and the geometry of the collision. In particle physics, high-energy collisions are typically studied using particle accelerators, which accelerate subatomic particles to very high speeds before colliding them with each other or with stationary targets. These collisions can produce a wide range of particles and phenomena, including the creation of new particles that may have never been observed before. One possibility is that in certain high-energy collisions, the energy of the collision is high enough to create a temporary concentration of energy that is so dense that it collapses into a black hole. This process is known as black hole production, and it has been a topic of speculation and research in particle physics for many years. However, it is important to note that the probability of black hole production in high-energy collisions is very small, and no such events have been definitively observed to date. In addition, the black holes that might be produced in this way would be very small and short-lived, and would evaporate through a process known as Hawking radiation, which would result in the emission of particles and energy. Overall, the study of high-energy collisions and black hole production remains an active area of research in particle physics, and may provide important insights into the nature of the universe and the behavior of matter and energy at extreme conditions. Accretion of matter onto a black hole is a process by which material such as gas or dust falls toward the black hole under the influence of its strong gravitational pull. As the material gets closer to the black hole, it heats up and emits intense radiation, making the black hole visible to telescopes and other instruments. The accretion process can occur in a variety of astrophysical contexts, such as in the vicinity of a supermassive black hole at the center of a galaxy, or in the formation of a black hole from the collapse of a massive star. The material that is accreted onto a black hole can come from a variety of sources, such as the interstellar medium or a companion star in a binary system. As the material falls toward the black hole, it forms an accretion disk, a flat disc-shaped structure that surrounds the black hole and is heated by the frictional forces generated as the material collides with itself. The accretion process can release vast amounts of energy, which can be observed across the entire electromagnetic spectrum. This radiation can be used to study the properties of the black hole, such as its mass and spin, as well as the properties of the surrounding material. In addition, the accretion process can have profound effects on the surrounding environment, such as driving powerful outflows of gas and dust that can shape the structure of galaxies and other astronomical objects. Overall, the accretion of matter onto black holes is a fascinating and important process that plays a key role in shaping the structure and evolution of the universe. Observational evidence for the existence of black holes comes from a variety of sources, including their gravitational effects on nearby matter, their accretion disks, and the emission of radiation from their surroundings. One of the most compelling pieces of evidence for black holes comes from the observation of stars and gas in the vicinity of a supermassive black hole at the center of the Milky Way galaxy. The orbits of these objects can only be explained by the presence of an extremely massive object, which is believed to be a black hole with a mass of around 4 million times that of the Sun. Another piece of evidence comes from observations of accretion disks around black holes. These disks can emit intense radiation across the entire electromagnetic spectrum, including X-rays and gamma rays. By studying the properties of this radiation, astronomers can infer the mass, spin, and other properties of the black hole. Observations of jets of gas and other material emanating from black holes provide further evidence for their existence. These jets can be observed at radio and other wavelengths and can extend for thousands of light years, suggesting that they are powered by an extremely energetic and compact object, such as a black hole. Finally, the recent detection of gravitational waves provides another avenue for observing black holes indirectly. Gravitational waves are ripples in space-time that are produced by the acceleration of massive objects, such as black holes. By detecting these waves, astronomers can infer the presence of black holes and study their properties in new and exciting ways. Overall, the observational evidence for black holes is very compelling and supports the idea that these objects are an important and ubiquitous feature of the universe. For more videos like this, please subscribe our channel, like, share, and press the bell icon. Thanks for watching.